Welcome to the third lecture of linear programming optimization. So today we are going to learn about graphical method of solving linear programming optimization problems. So the best advantage of graphical method is that you do not use any software like MATLAB or Excel VBA. You can easily solve the problem with just manual calculation and just by drawing some straight lines on the graph. So before starting, if you haven't subscribed my YouTube channel, please subscribe my YouTube channel to support me. Thank you. So this is our first optimization problem. So this is the optimization problem that we are going to solve with the graphical method of optimization. So linear programming optimization problem. So notice that all the equations are linear equations here. So the drawback of this method, the first and big drawback of this method is that it can only solve an optimization problem which contains only two variables x and y. So in this optimization problem, you can only apply this method if you have a problem with two variables only. Any two variable, it could be x1 and x2 or x or y. So this is our objective function of two variables 3 times x plus 4 times y, which is a linear equation. Now we want to maximize this objective function as well as minimize this objective function. So we will find the optimal point that will give us the maximum value of this objective function, and that will give us the minimum value of this objective function. So here are the constraints. So there are three constraints. So these are as here, and notice that all of these constraints are also linear equations. So I've already told you what linear equations are in my previous lecture. So please watch those lectures if you don't know what are the linear equations. So now the limits states that the values of x and y should be greater than or equal to 0. So which means we will be working in the first coordinate. All the values of x and y will be positive. So let's take our graph. So this is what our graph will look like. So here the values of x will also start from 0 and value of y will also start from 0, and they will go on increasing. So these are the positive values of x. So here we have our first constraint, which is 5x plus 4y equals to 200. Note here that the original constraint was less than or equal to 200. But first we will assume it as an equality constraint. We won't take the effect of inequality right now because we need to plot this equation on the graph, which will give us a straight line. So in order to plot this equation on the graph, we need 2 points, initial point of the line and the final point of the line, which is this one. So how we can find the initial and final point of this line from this equation? It's very easy. First you will put x equal to 0. That means you are on the y-axis. So it will give you a point on the y-axis. So in this equation, when you will put x equals 0, you will get the point of y, value of y. So now here this is your point 0 or 50 on the y-axis. And now after that, in order to find the final point coordinates, you will put y equal to 0. That would give you the value of x. So now you have 2 points, x and y, 0 or 50 and 40 or 0. So now in between those 2 points, you can easily draw a straight line. So now this straight line is for the equation for this equality constraint. But our original constraint was inequality constraint, which states that 5x plus 4y should be less than or equal to 200. So in order to take the effect of inequality constraint, what we will do, we will first take some assumed point either above this line or below this line, because inequality constraint means some portion or area which will satisfy this constraint, and that area can either be above this line or below this line. So first we will take any point in this area, in this region, any point. So I'm assuming a point of 5 or 5, which is somewhere here. So let's take that 5 or 5 point and put it into this equation, and let's see if this equation gets satisfied or not. So when we will put this 5 or 5 point into this portion, so it will give you the left hand side as equal to 45. So 45 is less than or equal to 200. So which means this constraint is satisfied. So that means this is our area. So all the points below this line will satisfy this inequality constraint, which was our original constraint. So now let's highlight that area. So this is the area. So all the points below this line will satisfy our this constraint, our first inequality constraint. In the same way, we will take our second inequality constraint. Our original constraint was less than or equal to 150, but first we will assume it as an equality constraint. We will simply, in the same way as we did previously, we will simply put x equals to 0 to get the initial point of this line. Now this red color line is our second constraint. So now we have our first point, and when we will put y equal to 0, we will get the value of x from this equation, and that would give us the second point, which is this one. So now we will make a line in this region, in this graph, and now we will have to see whether this was our original constraint. So which area satisfies this constraint, either above this line or below this line. So one of the area will satisfy this constraint. So we will take the same point as we did previously, 5 or 5 below this line, and we will see whether this point satisfies this original constraint or not. So here we are taking that same point and we are putting it into this equation. So it gives us the value of 40. 40 is less than or equal to 150, which means this constraint is also gets satisfied. So that means all the points below this line will satisfy this constraint. Now we need to take the common area, the area which was below this line and the area below this line, because both areas are below the line. So we will take the common area. So we will highlight that area. So this is the area. This area is below this line. So it's satisfying the green color line. And this area is also below this red color line. So it is satisfying this red color line as well. So now this is our common area. Simply we will take our third constraint. So our third constraint states that 5x plus 4y should be greater than or equal to 100. But first we will assume it as an equality constraint, and we will find the initial and final point, and we will draw that line. So now we have drawn that same line. This is the yellow color line is our this equation. So now we will take the effect of original constraint. So original constraint was 5x plus 4y is greater than or equal to 100. So we will simply take some point either above this line or below this line, and we will put it into this constraint, and we see if this constraint gets satisfied or not. Let's take the same point of 5 or 5 and put it into this constraint. So by putting 5 or 5 into this constraint, it gives us the value of 45. But 45 is not greater than or equal to 100. It is less than or equal to 100. So this 45 is not satisfying this our constraint, this third constraint, which means the area below this line will not satisfy this constraint. So it has to be area above this line. So now the area above this yellow color line will satisfy this constraint, this yellow constraint. So now we will highlight that area which will satisfy all three lines, all three constraints. So that is area below this green line, below this red line, and above this yellow color line. So this is the area. Now this area is satisfying all three constraints. It is below this green line, below this red line, and above this yellow color line. So now this is our common area. Now we have found our common area. So it is satisfying all the constraints. So our optimal solution must lie on this area. So it usually lies on the corner points. So the optimal solution must lie on the corner points. So there are 5 corner points in this area. Those 5 corner points are highlighted here. 1, 2, 3, 4, and 5. We already know the coordinates of 4 points. We already know the coordinate of this point, this point, this point, and this point. But we do not know the coordinate of this intersection point. This is also a corner point. So we need to take all the corner point coordinates. So first we will find this corner point coordinate. As we know that this is the intersection point of the green line and the red line. and we already have the equations of green line and the red line. So by solving these equations for values of x and y, both equation green line and the red line, we will get the values of x and y. So now we will find the intersection point of green line whose equation is 5x plus 4y equals 200, and from where we will write it in terms of x. So we are writing the green line equation in terms of x. So it will be in terms of x. Now we will put this value of x into the red color line equation. Red color line equation is 3 times x plus 5 times y. So we will replace the x with this value. So this value. So here we are replacing the x with this value, and we are putting it into the red color line equation. So now we will get our value of y. From by solving this equation, you will get our value of y. So by putting value of y back into this equation, we will get the value of x. So now our intersection point coordinates are 30.76 and 11.53. So these are the intersection point coordinates. So now we have found the coordinates all the 5 corner points. So the optimal solution must be one of these points. So the simply we will put all these points into our objective function, and we will calculate the value of objective function for each of these corner points. And then we will check which point gives us the maximum value of our objective function and which point will give us the minimum value of the objective function. So here we are doing this thing. Our objective function was z equals to 3 times x plus 4 times y. So now we will put the value of x and y. All the corner points coordinate, we will put it into our equation of z, which is our objective function. So it will give us these values. So by putting all these values into this equation, we will obtain these values. So now you can easily see that the first point gives us the minimum value of the objective function. So this is our optimal solution for minimization problem. If we were trying to minimize the objective function, this would have been our optimal solution. And if we were trying to maximize our objective function, this point, the intersection point, it gives us the highest value of the objective function. So this should have been our optimal solution for maximization problem. So this is it. This is it for today. Thank you for watching.